To the organizer for such a wonderful school and conference and for giving me the opportunity to speak today. So the results I will be talking about are in complex hyperbolic geometry, but they are actually related to the topic of the conference because they are in the applications part in the title, because my goal is to use some flat surfaces and a certain version of my class group in order to study complex hyperbolic geometry. So the plan of my talk will start will be starting with talking a little bit about complex hyperbolic space. Very briefly, just the things we will need. Then I will tell you why we need flat surfaces, what is the connection. So that are also in the title, the flat cone matrix and a sphere. And then I want to give you a geometric explanation of how those cone matrices are related to complex hyperbolic space. And finally, I will be talking about the actual result. That is that using these, I will be building some fundamental domains for some lattices in complex hyperbolic, in the isometries of complex hyperbolic space. So the complex hyperbolic space is the analogous of the real hyperbolic space. That so when we want to talk about the real hyperbolic the real hyperbolic space, we take the form x1 squared plus x2 squared minus x3 squared, and then we make the cone where this form is 0. And then we projectivize. So we take one point per vector of the ones that are inside, because inside this form is negative, on the cone is equal 0, outside of the cone is positive. So we take the subspaces where it's negative, and we projectivize it. And we want to do the same thing, but in a complex setting. So we start from Cn1, a complex vector space of dimension n+1, and we call it Cn1 and not Cn+1 because we put on it a Hermitian form H, which has signature n1. So where Hermitian means that the conjugate of the transpose is the same as the matrix itself. And this allows us to define a product as W star, where stars means the transpose of the conjugate, times H times Z. And the most obvious example that is similar to the ones where we have here is to take H to be 1s and 1 minus 1. And then we divide the space into what we call V plus, V0, and V minus, that are the Z in Cn1, such that the product of Z and Z is positive, 0, or negative. Positive if we are in V plus, 0 if we are in V0, and negative if we are in V minus. Then we consider the projection of Cn plus 1 minus 0 onto Cn. And we define the complex hyperbolic n space to be the projectivize of the subspace V minus, because this projection preserves the subspaces, so we can do that. And on this we put a metric, that is that the hyperbolic cosine of the distance between 2 points over 2 is defined as the product of the 2 points over the product of Z with itself and the product of W with itself. And it's different from the real hyperbolic space for a lot of reasons, but in particularly, the curvature is no longer constant, so a lot of difficult thing happens, which makes it interesting for me. In here, we will consider the space of isometries. That is the group generated by the complex conjugation and by PU of H, which means that we're taking the unitary matrices with respect to H, and then we projectivize it. This is called U of H. And in here, I will be interested in studying lattices. And I remind you that gamma in Pu of H, that sometimes is also called P11, since it doesn't depend on which particular H we choose. So this is a lattice if we have 2 things. One is that gamma is discrete. And the second is that the volume of H and C quotiented by this group has finite volume. OK, and I think this is all we will need about complex hyperbolic space. So I will pass to the second part. So what I will be studying, the kind of flat surfaces I will be studying, are the cone matrix on a sphere. So what does this mean? Well, it means that we have a surface that is locally R2, except for finitely many points, where a neighborhood looks like a cone, where those 2 are identified. This is the point around which we're doing, and it's this part here. And so a cone point will have a cone angle theta and a curvature alpha. So P will be a cone point, theta will be the cone angle at P, and alpha will be the curvature at P. And those will need to verify that the sum of the curvature is 2 pi times 2 minus 2g. That is the discrete version of the Gauss-Bonnet formula. So a remark, in general, this worked for any theta, bigger, smaller, and in fact, until last week, we always had a multiple of 2 pi or multiple of pi. But here, today, we will always have theta smaller than 2 pi. So we need to forget everything that we heard until now, and we need to think of the cone points to be actual cones, smaller than 2 pi. So obvious examples. Well, we can take a cube. We need to smoothen up the edges, but we can do that, and it's OK. And we remain with 8 cone points, 8 cone singularities, given by the vertices that have angle 3 times pi over 2 around. And in general, polyhedra are also example of cone metrics, but there are also other examples. So one that will be important to me is a pillowcase. So a square pillowcase is just obtained by 2 squares glued along the boundary, so empty inside, so we can put the pillow inside. And here we will have 4 singularities and with pi as cone angle in each of them. Okay? So then one can fix the cone angle, fix the values of the cone angles, and study the configuration of the cone points. So now we are on a sphere, and yes?
So I'm not quite sure. So you've already got a metric on the sphere?
No. These are two different parts. So first I define you what the complex hyperbolic space is, and now keep it in mind because we'll need it later. But for a moment, forget about the complex hyperbolic space because it will appear in my next theorem, but not yet. So now, if you forget for a second about this, and think of cone metrics on the sphere when we fix the cone angles. So the point will be that if we fix the cone angle and we study the configurations of cone points, so their positions on the sphere.
When you say sphere, you mean a complex sphere?
A sphere, just a surface. Yeah. A topological. Fine.
Two-dimensional topological.
Two-dimensional, yeah.
Real.
Real dimension too, yes. Oh, thank you. Yeah, two-dimensional, definitely. So the reason why those two things are connected is a theorem from Thurston's. That basically says that if we fix the cone angle and we study the configuration of cone points, then we have a complex hyperbolic structure on this space. So more precisely, we take endpoints and real numbers such that they are between 0 and 2 pi. Their sum is for pi. That is the thing that we said that we want to consider. And then the set of cone metrics on a sphere of area 1, cone angles equal 2 pi minus the alpha I, so such that they have curvature. The alpha i's is a complex hyperbolic manifold of dimension n-3. But this is not complete, which we don't really like. But its metric completion is a complex hyperbolic cone manifold. And moreover, this is an orbifold in some cases. If the alpha i's verify some conditions which I don't really want to talk about, but they are like just simple conditions on the alpha i's, or some sums of them dividing or not dividing 2 pi. With yeah.
This definition maybe it's a good overfold.
So it's the quotient by a discrete group, yeah. So in this way, Thurston gave an alternative description of the Deligne-Mostow lattices. They are the things we need to quotient in the complex hyperbolic space by to get those orbifolds. And that had it's not quite clear to me because it depends who I ask, but who did it first. So because Thurston's paper came out a lot later than he wrote it. So most people say that they discovered them at the same time. But I think that Deligne-Mostow Thurston is too long. So I'll just call them Deligne-Mostow. So they introduced them in the 80s using monodromy of hypergeometric function, which I don't know much about, but that's how they gave it in the first place. But I like geometry, so I like a lot more Thurston description of the same lattices. OK, so some remarks. First remark, the Hermitian form that we need there, yes?
When you cone metrics, you mean up to nothing?
I mean?
Up to nothing.
Yeah. Yeah, I'm fixing the cone angles. So so we are changing the position of the cone points. That's all, and we are asking for the area to be 1. But I mean, the third part will be giving an explicit geometric construction that show why this is true. So
there's a finite set of cone metrics.
Yeah.
Cone
No. What? Yeah, outside of the cone point is flat. That's what a cone metric is. OK, so the Hermitian form that we need to define the complex hyperbolic structure is given by the area. And so automorphisms of the sphere, since they preserve the area, they are in PU n minus 3, 1. And the incompleteness is given by the following phenomena, that is that we could have 2 cone points that approach and get closer and closer until eventually, like giving a Cauchy sequence, until eventually, in the limit, they coalesce. But we're not anymore in the same space because we have 1 cone point less. And we had fixed the number and the angles of the cone points. So up to adding, so the making the metric completion will mean adding those kind of points. Yes?
How many lattices are described by this?
So in all dimension, they were 70, I think?
94.
94, sorry. Yeah.
With 5 or more points.
Sorry?
94 with 5 or more points.
Yes. Yeah. So I mean, the case of dimension 1, the complex hyperbolic 1 space is the same as real hyperbolic 2 space, while that's not true in higher dimension. And then, so yeah, he gets a finite amount. And I've been studying the one in dimension 2. So soon we will reduce to the case of when we have 5 cone points. So what version of the mapping class group we use? Well, usually the mapping class group allows to permute cone points, to permute singularities. The pure mapping class group doesn't allow to permute cone singularity. And here we will allow to swap 2 cone points if they have same cone angle. Okay? So those are the kind of maps we will use. And so from now on, we will consider 5 cone singularity, the number of cone points, And since the dimension goes down by 3, we will be in H2C, and lattices in Pu2 1. Okay? So in the third part of my talk, I want to see why this is true. So this is not quite how Thurston proved it, but it's a construction due to Parker, my supervisor. But it's nice because it's very geometric, and we will get some coordinates to describe all the possible position of cone points, and we will see why this has a complex hyperbolic structure. So fix the cone angles. So fix theta 1, theta 2, theta 3, theta 4, and theta 5. And now we want to consider all the possible positions of the cone matrix with those cone angles on a sphere and parameterize this space. So first easier case. So this is not general. I'm not describing all of them. I'm just describing a small amount, is when we have a pentagonal pillowcase. Which means that the points are all on the equator of the sphere. Okay, so this is a first easier case to describe, and then we will see how to generalize it to the general case. So what I'm saying here is that I have two isometric Euclidean pentagon glued along the boundary and with smooth edges. And here we will have at V1, we will have angle theta 1, V2, sorry, I want to call them V star, V0, V1, V2, and V3. So we will have angle theta 1, theta 2, theta 3, theta 4, theta 5. Okay? So what do we do? The first thing that we do is to get colors. So the first thing that we do is that we cut along those curves between the cone points, leaving half of the angle on one side and half of the angle on the other side. And then we open it up and we flatten it down on the plane. So we would get something like this. From which we can recover the cone matrix by gluing this on this, and this side on this side, and this side on this side, and the last two together. And now I continue these lines. And I say, well, if I want to describe this blue part, big pi, I need to take copies of this big triangle, not quite a triangle because I'm not that good at drawing, and remove from it those two small triangles, and then remove also those two small triangles. Okay, and then I get exactly the blue part. But then all the angles are all a specific quantity, because this angle is half of the cone angle at this point, and so on. So all the angles we know. We know the values of all the angles, because so this will be theta 1 over 2, theta 2 over 2, and so we can get the angles of everything else. And so this means that to describe the three triangles, we only need one side, because given one side and all the angles, the triangle is perfectly identified. So we take those three aligned vectors to be x1, x2, x3. And so if we give three numbers, we can make a construction like this, glue it up, and get a cone matrix. And if we have a cone matrix, we can open it up, build the three triangles, and give three real numbers that are the length of those three vectors. Sorry?
How do we get
To a cone metric. So if I know three numbers and the angles, because the angles are fixed, yeah. Okay? Yeah. And then we also want to say that the area of the blue part is the area, so let's call the big white triangle T3, and then this one T2, and this one T1, with their correspective T-1, T-2, and T-3. Well, if I want the area of pi, then I need to take twice the area of T3 minus the area of T2 minus the area of T1. And those areas can be given in terms of our coordinate as a certain constant that depends on the angle times x3 squared minus another constant that depends on the angles again, x2 squared minus c times x1 squared, which start to look familiar, look promising. But now let's look at the general case. So the fact that we were asking for all the points to be on the equator, it means that we can cut and leaving a half of the angle on one side and half of the angle on the other side. So what we're saying is that the next cone point is such that half of the angle is here and half of the angle is here. But in the general case, we need to think that we can have something that we have this cut, but the next cone point could be down here, not necessarily on this equator. So we could have to leave a small angle on one side and a bigger angle on the other side. Now, I'll do a picture of how this changes, and I promise you that if you look at it long enough, you'll believe me. And that is that if I build the same triangles, but this time, instead of having x1, x2, x3 aligned, I change the direction. And so x1 will be here, x2 would be here, and x3 would still be this one here. Then that's exactly what I'm doing, because let's recover pi. So we start from up here, and then we go to the red triangle, then we go down to the green, and then we go back to the other red one, and we get this. So this angle needs to change as much as this one, because otherwise I won't have same length there, and I can't glue it back. And now what happened? Well, here we had that if we consider this starting point, half angle is on one side and half angle is on the other side. And here, if we do this, well, we have a small angle alpha on this side and a big angle beta on the other side. And this is true for all the angle. And so tilting the triangle more and more, we can actually get all the possible cone metric, all the possible position of the next point. And like this, we can describe all the cone metrics. So now our coordinates will be called z. Because they're not anymore aligned, so they're not anymore real, and they're vectors, so they're complex numbers. So the variables become complex. The area is given by the same formula, up to here taking the modulus squared. And so my claim now is that this has a complex hyperbolic structure. Well, what did we need that we know up there? So first we needed C 2, 1. And here we have 3 complex variables. And we need it in a Hermitian form. And here we can take the area to be the Hermitian form. So A, B, well, A minus B minus C. And then we want it to take the subspace V minus. But well, if the area is negative, the sphere doesn't make sense at all. So clearly we want to ask for the area to be positive. And then we want it to projectivize. But when we projectivize, we're just saying that up to rescaling, we're considering it to be the same cone metric. And so it's the same asking for the area to be 1. Or equivalently, we can also choose another renormalization, and we can ask for Z3 to be 1. That is why I kept the white triangle fixed, because this is a more comfortable renormalization for me. OK? Any question? Yeah?
How do you get the pentagon regional? Is it intrinsic to the metric? The pentagon?
Yeah.
How do you get
It from this picture?
Yeah, but in the other direction, from a metric.
From a metric. Well, I do the same thing. I give an order to the cone point, and I cut along geodesics.
Okay,
Yeah. And then I open it up and flatten it down on the plane. Yeah. OK. And so we have, in some sense, our complex hyperbolic space to be the Z. And we can choose the normalization Z1, Z2, 1, such that the area of pi is bigger than 0. And so this is exactly what Thurston's theorem said. OK. Good. So my goal now, yes?
Is this type of analysis also possible for larger N, or is this specific to this one?
Oh yeah, yeah. I mean, I can for 1 dimension up, it's easy really. Like we just need to ask another triangle here on the top. For higher, I haven't thought about it, but I'm not sure we can do it like with triangles, but surely we can give a polygonal presentation. So one of my projects is actually to try to do the same thing in 1 dimension up, for example. So the goal now is to study lattices in Pu2-1. And this is kind of hard, and I want to give you an idea of why this is hard. So in general, it's interesting because we have relatively few constructions. In particular, few constructions that don't come from number theory, so that they're not immediately obviously arithmetic. And one of the reasons for this is that building fundamental domains is hard because there are no totally geodesic real hypersurfaces. So basically, what we would want to be the walls of our fundamental domain are not totally geodesics. So the geodesics don't stay inside the walls, which makes it really hard to glue them. It makes it really hard to do a lot of things. And a substitute that is used sometimes is the one of bisectors. That is the one that I also used. A bisector is the locus of point equidistant from 2 given points. And those are foliated by totally geodesic subspaces in 2 different ways. And we know a lot of how they intersect. So they're nice subspaces that can be used as a substitute for totally geodesic real hypersurfaces. Because they're not totally geodesics, clearly, but they still have some nice properties. So once we have this construction, and we want to build polyhedra, then the idea of what I will be doing is that I will find a candidate polyhedron by thinking of how the metric completion is built, by thinking of when those this construction give the same metric, really, and then use Poincaré-Polyhedron theorem that says that if I have a polyhedron and I have a set of maps called side pairings, because, well, they pair the sides, and if those satisfy certain conditions, which, I mean, they're very intuitive. There are some finiteness condition, some cycle conditions, and I mean, well, we can talk about it later, but there are a lot and they're somehow technical. Well, then I know that the group generated by those Ti is discrete, and D is a fundamental domain for it. And D is also allowed to give a presentation for the groups. So fourth part of my talk, how do we build those polyhedra? So the first thing we do is that we start looking at what happens when pairs of coins coalesce, because in this way we're kind of like moving towards the edge of our space. So when we make two pairs of points coalesce, then we get some vertices. We start studying their coordinates in terms of Z1, Z2, and Z3. And then based on this, we build a polyhedron. So considering what happens when con points coalesce, we get to define a polyhedron that is very nice in our coordinates. And so in coordinate Z, and we will need another set of coordinates that we call that will be a certain matrix that I will explain in a moment what it is. So, but they are linear in the Z coordinate, and then in those two sets of coordinate we have very nice description of polyhedron only in terms of the arguments. So the argument of Z1 needs to be between -phi and 0. The argument of Z2 between 0 and theta. The argument of W1 between 0 and phi. And the argument of W2 between 0 and theta, where theta and phi are given in terms of the con points that we had at the beginning. And a priori, they don't completely describe the lattice, but in some cases they do. And we will see. I will explain in a moment what I mean. So what happens is that when we give, so we know from Deligne-Mostow and Thurston a finite set of initial angles θ1 to 5 that give orbifolds. So, and of those, they all have a certain symmetry. So they either have threefold symmetry. That means that three of those cone angles are the same. Or twofold symmetry. That means that only two of those cone angles are the same. So first of all, we will look at the threefold symmetry case, because the more symmetry we have, the more intuitive maps we have, the swap cone points. So this is the case that has been studied the most before me in these terms. Okay. So threefold symmetry. So we have V1, V2, and V3 that have same cone angle. And so we can swap them, and we can get some maps that we call the moves. So R1 swaps V2 and V3. So we have two cone points with same cone angle, and we basically take a curve around them, and we're doing some sort of half-done twist. So it's like we detach a little piece, we turn it around, and we glue it back. Of course, this would not be smooth, but you know what I mean. And then we have a second map, R2, that swaps V1 and V2, that again have same cone angle. So we swap them. And then we want another map that we call A1, and sends V1 back to V1, but passing around another cone point with a different angle. So say V4. Okay? And in this case, it's more like a full-done twist. And then consider the group generated by R1, R2, and A1. Sorry?
Can you explain the map A1
It's a then twist around a curve that passes around another cone points with a different. You can imagine it as if we want to swap it, but then if we swap them, we would not be in the same cone metric, so we swap them again. So we take it all the way around and then back, fixing these cone points and sending this back to this, but passing around this other cone point. Okay? And as it happens, this works. So as we just defined, with theta angles in the Deligne-Mostow Thurston list of lattices with threefold symmetry, so gamma generated by R1, R2, R1, R2, that is the P that we used for the coordinates, and R1, R2, A1, which is the same group as the gamma that we considered here, but I'm giving those as generators because they are my side pairing maps. Well, then gamma is discrete in PU1, 2, and it has fundamental domain. Well, not quite D, but a certain modification of D. So parts of these theorems have been done by different people, because those lattices can be divided according to the values of the cone angle in 4 classes. So the one that I call the first type, second type, and third type, and fourth type. So the first case that has been considered are the one of second type, and the fundamental domain was built by Derot, Falbel, and Popper in 2005 with a different construction from this one. And well, it's not quite D, but it's D with 1, 2 facet collapsing to a point. So it has almost the same combinatorial, except that a facets of dimension 2 that is triangular is collapsed to a single point. And then Parker considered the lattices of third type in 2006. And that's where he came up with the nice parametrization of the cone matrix that I described earlier, where we have two facets collapsing. Collapsing, I always mean to a single point. And then Boadi and Parker in 2015. Similarly, for two facets collapsing to a point. And they're actually those three, this one. And that's where I started working on the topic. And I started looking at this other case. And so the first thing I did is that I did the same thing, and I found that this was D, which has two interests. One interest is due to the fact that now we have a complete picture of all the threefold symmetry lattices. And the other is that before, we had different combinatorics for those three, but it wasn't really clear how they were related exactly. So for this one, we could see that we needed to collapse the same three facets that are collapsed here and the same that are collapsed here, but somehow they were different polyhedra. They were kind of separate. And so one of the nice things of having this other one is that now we have a single polyhedron, and all the other ones can be obtained by just deforming a little bit the one that we have in this case. And so basically what we did with this work so we reproved the discreteness, which we already knew from Deligne-Mostow and Thurston, but it's always nice to see that we agree. And then we were able to give a presentation that was kind of included in Deligne-Mostow's work, but it wasn't explicit. And then we could also recalculate the volumes, which, again, other people calculated it already before, but we found the same values again. Okay. And then we go to the twofold symmetry case. Okay. So in the threefold symmetry case, when we had those configuration of triangles, we had chosen those three angles to be the same. And now what I do is that I think of three cases. That is when we have those 2 points to be the same, case 1, or those two to be the same, or those two to be the same. And for each of those, I can do the same thing, and I can obtain a polyhedron. But they will be different polyhedra, D1, D1, D2, and D3. And if we think about the moves, so for each of those, we will have a set of moves. But now, so R1, that was swapping those two, well, if we are in configuration 2, then it's an automorphism of the sphere. But if we're not, then we pass from a configuration of type 1 to a configuration of type 3, because we're swapping those 2 compoints. So the 2 compoints will be here, and we have type 3. And so for each of those types, we have an R1, an R2, and an A1, that before they were pairing the sides of the polyhedron, and now not quite. Now if we consider the union of this polyhedra? Well, I can't really quite draw in 4 dimensions, but they will look something like this. So here we will have our D1, here we'll have our D2, and here we'll have our D3. So they will have a 2-dimensional intersection where all 3 of them intersect. But now, like these not very accurate pictures, I want to give it to you because, so we had some side pairs, so we keep some sides, the ones outside here, and some others now they're in the middle when we glue them. And so what we do is that the sides that we keep, we still keep the side pairing, and those are the side pairing. So in R1, R2 was swapping those 2. So R2 was exchanging 2 sides, and now we remain of the same type, so we keep the move. While when we had R1, when we are in type 1, we end up, let's say, let's change this, then we end in type 3, and then we had another map that before would have paired those sides. Now it doesn't, but we can take the composition, and then we could consider that as a side pairing, and it would pair a side that is here and a side that is here. And this is basically the same as saying, well, now this compound is different, so we swap it once, and so in some sense we apply this, but not quite, because we end up outside our space of cone matrix, and then we do it again. And so we get this composition. And those will be our new side pairing. So by keeping some of them and by composing some other of them, we get a set of maps. And well, this works. So for initial angle in Deligne-Mostow or Thurston's list, and up to collapsing some 2 facets like before, the polyhedron D union and the set of those TIs that I mentioned satisfy Poincaré polyhedron theorem. So the gamma generated by the TI is discrete. D star up to collapsing is a fundamental domain. And we can give a presentation. And it's too long and not very meaningful to write, so that's it. Okay, so I think I can stop here.